But I do want you to know about the average value of a function. If we're given a continuous function f on a closed interval from a to b, I want you to know the definition of the average value of f over the interval from a to b. Forgot to mention this with the first section, but I want to also denote this by a special symbol, f bar. This symbol is not a universal symbol for the average value. Some people write f sub AVE for average. I like f bar. It's kind of similar to symbols used in statistics for averages. Turns out to be defined to be 1 divided by b minus a times the integral of the function. And by the way, when the function is continuous, you can prove the integral does exist. It makes sense. There are some really weird discontinuous functions where integrals can't be defined. They're really, really weird. But we don't really typically deal with really, really weird functions in this class. This is somewhat similar to what you do with averages in statistics, right? Pretend you're a basketball player, you play 20 games during a season. You're wondering, how many points did I average every game? What do? You add up all your scores from each game and you divide by 20, the number of games. It's kind of similar to that. The integral is like adding. And here we're dividing by b minus a. That's analogous to dividing by the number of games. It's not the exact same thing by any means. It's just similar. More importantly, you should know how to interpret this geometrically. And the way to do that is to first take this definition equation and multiply both sides of it by b minus a and rewrite it as f bar times b minus a equals the integral. You also could switch the sides here. You could say the integral is f bar times b minus a. And the geometric interpretation of this is important. Let's say our graph is increasing in concave up, just like our example was, but I won't say it's our example, x squared example. Let's say it looks like that. The integral, of course, represents the area under the curve. The area of that is the integral. F bar, the average value, is a number that can be interpreted as a height of a rectangle with base from A to B, whose area is the same as the area under the curve. B minus A is this length right there. If I make a rectangle with a height chosen appropriately, maybe about this high, so that the area of this rectangle is the same as the area under the curve, then that height right there, that's going to be F average or F bar. This is F bar here. F is a function, F bar is a number. That's a little confusing with the notation. F is a function, F bar is a number. That might not seem like such a big deal, but it is a pretty big deal. It does have real life applications, or it can be interpreted in terms of real life at least. Pretend you're in a car driving down the road and you're kind of, you like to speed up and slow down a lot. Actually, I was in a car with somebody who was doing that, not on purpose. They weren't falling asleep either. That's just the way they drove. They'd speed up to 80 miles an hour, slow down to 50. Speed up to 80, slow down to 50. He was a very talkative person. I was in the car with other people. They were all talking. It's like, can you please turn on the cruise control or something? So you speed up, slow down, speed up, slow down. You are going to get somewhere, but your velocity is not constant. If you can figure out your average velocity, that'd be the same velocity somebody could set the cruise control at to go the same distance in the same amount of time. That's an interpretation of it, at least. More importantly to me, typically, is if you take multivariable calculus, the idea of average value generalizes to other kinds of functions involving other kinds of integrals that are harder to understand. Double integrals, triple integrals, quadruple integrals, quintuple, hextuple. Okay, we stop at triple integrals. But then we also do what are called line integrals and surface integrals, which are the hardest to understand. The idea of average value can help you understand them. I think is real key to helping you understand the meaning of those line integrals and surface integrals in multivariable calculus.